Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T, and today I have a tutorial introducing you to sequences and series. This will be the first tutorial in our unit on sequences and series. So let's get started. Let's talk about the word sequences. Sequences is a list of numbers that have some sort of pattern. We can have a finite sequence, meaning there's only a specific number of items, or it can be an infinite sequence, meaning we have a pattern, but that pattern continues forever. Usually we assign a name to a sequence, and we'll be frequently using the name A to represent all the numbers in a sequence. Now, one of the things we're going to be doing is writing rules for the sequence. Now, the most useful rules that we'll be focusing on are the explicit rules, but the easier ones to write are recursive. So let me give you an example of what I mean by a recursive rule. So to write a recursive rule, the first thing we look at is we try to find the pattern. Now there's going to be some common techniques that we will look at when trying to find the patterns. Now some of you may have already noticed in this sequence here that going from the first item to the next, we've added 3, we've added 3, we've added 3. So in this particular case, what we're looking at is a common sum or a common difference. You'll hear the word in an upcoming video about common difference. So instead of adding here, we would be taking this item minus that one. So 5 minus 2 would be 3, 8 minus 5 would be 3. That would be our common difference. So to write a recursive rule, we will identify the starting number. So we're going to use A as the name of our sequence and little subscripts for the term. This is the first term, second term, third term, fourth term, fifth term. So when we write a recursive rule, we have to specify our starting term and then our next term, or the nth term, in this case, is the previous term plus 3, our common difference. So if we're trying to find, so for example, if we were trying to find a sub 2, we were specified a sub 1, that would be a sub n minus 1 would be a sub 1 plus 3, which would be, and we specified that a sub 1 was 2, and we get 5. A sub 3 would be a sub 2 plus 3, which is the previous one, plus 3 is 8. Now the problem with a recursive rule is if we wanted to find the 50th term in a infinite sequence, for example, we would need to know the 49th. To find the 49th, we need to find the 48th, and so forth, so you have to find them in order. In explicit rules, we're going to write a formula. So kind of what we could look here is on, if this is term number 1, we haven't added any 3's. On term 2, so this is the term number n, so we've added 0 3's. Here we've added 1 3. On team 3, we've added 2 3's. So you can see we've added 1 less 3 than the term. So we could write our rule as being the first term plus some number of 3's. And the number of 3's we're going to add is going to be 1 less than the term. So here we've had 0 3's. So this was 1 3, 2 3's, 3 3's. So each time we've added 1 more 3, so that's multiplication. So we could then simplify this explicit formula by distributing our 3 and combining our like terms. So 2 and negative 3 is negative 1 plus 3n. So you could see if we wanted the fifth term in this sequence, we could just plug in 5 for 3. I'm not for 3, for the n. And that's going to give us 14, which was the 1, 2, 3, 4, fifth term. So over here, if we look at the differences, here we're subtract 4, here we're subtract 4, subtract 4. So again, this has a common difference. And I'm going to skip over the recursive rules. We're going to focus on that later. We really want our explicit rules. So again, here we've added 0 fours, we've subtracted 1 4, 0 fours, we've subtracted 1 4, we've subtracted 2 fours, we've subtracted 3 fours. So like the last one, we're going to have our starting amount, and the number of fours that we will be subtracting will be the number of terms minus 1. And again, we could simplify that by distributing our negative 4 and combining like terms. Now, some other types of sequences here. The pattern here, if we look at common differences or common sums, here we have plus 1, plus 2, plus 4, plus 8. So it's not a common term. So another thing to look at besides common sums or common differences, so that's one thing to try. The next one is to look at common multipliers. So here you can see going from here to here, we've times it by 2, and then we've times the previous number by 2 and by 2. So our recursive rule, our first term would be 1, and then to get the next term, we are taking the previous term times 2. Again, if we're looking to write the explicit rule, we can count how many times we've multiplied by 2. So the number of times we've multiplied by 2. So on term 1, we've multiplied 0 times, 1 times, 2 times, 3 times. So again, the number of times we've multiplied by 2 is 1 less than the term. So here we're going to have our first term times, now repeated multiplication is an exponent, so this is going to be 2 to the n minus 1 power. And we don't really need this 1 here, so for the sequence on the left there, we could, again, if we're trying to find, say, the 7th term in the sequence, it would be 2 to the 7 minus 1, which is 2 to the 6th, which is 64. So this would be the 1, 2, 3, 4, 5. So the 6th term would have been here 32. So it looks like I messed up. Oh, we were doing the 7th term. So the 6th term would be 32, and the 7th term would be 64. Here we can see the common multiplier is we're dividing by negative 3. When you see alternating signs here, well, that's not quite right. There's oh yes, they are alternating. So plus, minus, plus, minus. So we're dividing by negative 3, dividing by negative 3, or multiplying, we're multiplying by negative 1/3, multiplying by negative 1/3. So we can identify that pattern. Now there are lots of different rules or patterns that you will explore or you will discover as we explore sequences. So one more is one of the most common ones, or not most common, but it's widely used. You can research on Google about the Fibonacci sequence. It shows up. People see evidence of that in nature in a lot of places. But if you look at this, there's not a common adding and there's not a common multiple. But to get a number, once we get out here to the third number, it's the sum of the two previous ones. So 3 is the sum of 2 and 1. 5 is the sum of 3 and 2. 8's the sum here. So our next number would be the sum of 8 and 5. So our next number would be 13. And then 13 and 8 would be 21. and then 21 and 13 would be 34, etc. And I've shown here the recursive rule for the Fibonacci sequence. It's very difficult to write. It may even be impossible to write an explicit sequence for the Fibonacci. If there is one, it's very complicated. So we're going to go through now some of the sample problems from the practice worksheets and exit tickets that you'll be doing. So again, we need to first identify the pattern. So you can see here it looks like we are multiplying by 6. Multiplying by 6. So it's asking to find the next 3 terms. So we would here be multiplying that by 6. So that's going to be 12, 54, 55, 35, 12, and 3 would be 15. So negative 15, 552. I should have picked one here where I could do the mental math. I'm not going to keep it. We would just keep multiplying by 6. Here, this one's more complicated. We're not adding 3's. We're not multiplying by something. We're not adding the previous 2. But if we look at this, I could see if I take 1 squared and subtract by 1, I get 0. If I take 2 squared and subtract 1, I get 3. If I take 3 squared, because this is term 3 minus 1, I get 8. So this one's going to be the term. So this one's going to be, to get to the next term, it's going to be n squared minus 1. So this was term 1, 2, 3, 4, 5. So this would be 36 minus 1 would be 35. This would be 7 squared minus 1, 8 squared minus 1. So it's the squares minus 1. If we are given the explicit formula for a sequence and it's asked to find the first 4 terms, it's just asking you to plug in n equals 1, 2, 3, and 4 and list them. So if we put in n as 1, we've got 10 to the first, which is 10 minus 3 would be 7. If we put in 2, 10 squared is 100, minus 3 would be 97. 10 cubed would be 1,000, minus 3 would be 997. And 10,000 minus 3 would be 9997. Over here, we're going to be squaring in and subtracting 3. So the first term would be 1 squared minus 3 would be negative 2. 2 squared minus 3 would be 1. 9 minus 3 would be 6. And 16 minus 3 would be 13. Sometimes we may just want to find a particular term way out in the sequence, so this is asking us to find a sub 10. So we're just plugging in. So we get 20 over 12, which could be reduced to, those are both divisible by 4, so 5/3. You can use the frac button on the calculator to simplify that, and here if we do the 10th term here, a sub 10 would be 2 times 10 minus 1 squared, so that's going to be 19 squared, and I don't have a calculator up, so we could just calculate that number. All right, so that's sequences. Oh, I'm sorry, we have one more here. We've got to write a formula. So here you can see we're adding 4, adding 4, adding 4. You'll learn in our next lesson that this is something called an arithmetic sequence. And remember when we did this earlier, we've added 1 less 4 than the term. So here we've added 0 4s, 1 4, 2 4, 3 4, 4 4s. So we've got 26, and we've added 1 less 4 than our term number. And we can simplify this by distributing our 4 and combining like terms. Oops, that's an n there. That would be our explicit rule. Here we can, if you look at it, we can see we're multiplying by 1/3. We're multiplying by 1/3, and again, the number of 1/3 is 1 less than n. So we would have 18 times 1/3, and the way we do repeated multiplication is exponents. Now those were lists of numbers, so now we're going to talk about series. Series is when we take that list of numbers and add them all up. Here you can see something from geometry called Sierpinski's triangle. We could be adding up as we go through the stages how the area, the white area, is growing. The sum of all those triangles. So if we have a sequence and we turn it into a series, we are just adding those items up. We can have finite series where we add a specific number of terms and we will get a finite number. And then we have an infinite number of terms, which in this case would add up to infinity. There are some infinite series where we're adding an infinite number of numbers that add up to a finite number here. It'll be kind of weird, and we'll talk about that in a later video. Frequently when we're dealing with series, we use something called summation notation. Sigma. Sigma stands for summation. And what we have is a rule of what we do with a number, and the numbers start at the bottom number and go to the top number by adding 1. So if I wanted to expand this out, I would put in 1 first, so this would be 3 times 1, and then 3 times 2, and 3 times 3, 3 times 4, and 3 times 5, and we would stop when we get to the 5. Now we would just have to calculate all those numbers. And then we would have to add them up. So we've got here 27, 36, 42, 45. This one we would keep going forever, so it would be an infinite series. I'm not going to do that one out. And then this last one, we would plug in the I for both places. So here we would have 1 over 1 plus 1 is 2. And then 2 plus 1 would be 3. And we're going to do this 5 times. And then you could get a calculator and you could add those numbers up. So this is called sigma notation. So let's work a couple problems similar to what you'll have on your exit ticket and worksheet. So again, first step would be to expand this. So our first term, so again, we're going to plug in k equals 1, 2, 3, 4, and 5. So when we put in 1, I've got 4 times 1 squared is 4. We get 6, and then we're going to add all those together. So if I put in 2 here, 2 squared is 4. 4 times 4 is 16, plus 2 is 18. If we put in 3, I've got 9 times 4 is 36, plus 2 is going to be 38. 4, I've got 16 times 4 is 64, 68. And 5 here is 25 times 4 is 102. And then we just have to add those numbers up. So let's see if I can do that in my head. 170, 208, 226, 232 if I did that correctly. Now down here, most of the time we start at 1, but we don't have to. So here we're going to start at 3. So this is going to be 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. And then we would calculate each of those. And add them up. And I'm not going to add those up. You can pull out your calculator and add those up for me. So that's it for our introduction to sequences and series. So remember, sequences is a list of numbers that has some patterns. So our key skill is discovering those patterns and writing rules. And then series is when we sum up a pattern, and we have learned about the sigma notation. So good luck working your practice worksheet.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you